This week you will be using 2 burettes. Each burette contains a colorless and a clear liquid, so you will need to label which one is which. Dry erase board marker works really well on the base of the burette stand, or you can just simply put the bottles directly by those burettes so you can keep track of which is which. Make sure that once you have filled your burette, you remove the funnel. A funnel on the top of the burette can drip liquid and can cause problems for your measurement.
Record the initial reading for both burettes, making sure to remember to designate which one is the acid and which one is the base. It may be helpful to use a note card to have either a white background if the markings on the burette are dark, or a black background if the markings on your burette are white. Remember that to read a burette, you're reading from the top down. This measurement is between 7 and 8 milliliters. So we would say 7 point and then count the lines from the 7 to the 8. So here's the 0.5, 0.6, 0.7. So this is roughly 7.8. We have the ability to estimate the next decimal place as well. Begin by adding 11 to 14 milliliters of your acid to the flask. Take note of where the initial measurement is, and then calculate how far that will need to be in order to get to your 11 milliliters. And then simply stop when you are in that ballpark. Then record the volume of this measurement as well. You will need to add several drops of Phenolphthalein Indicator to your flask. Indicator sometimes is rather weak, so you might need to do 5 or 6 drops. It won't change colors now, but it will change color once it has gone from an acid to neutral and just into the base range. Now you will begin adding your base. You can initially add a good 10 milliliters, as you're going to need at least 10 milliliters for this titration, so you don't have to go real slow at first. You can see that the solution is turning pink at this point, but if I swirl the liquid, that pink goes away. So what I'm looking for is a persistent pink, a pink that stays even after I have swirled the solution. So I can continue adding a few squirts at a time, and as long as the solution rapidly turns to a clear color, then I can keep adding the solution. Once it becomes more difficult or to get that color to disappear, then you're going to need to add smaller amounts. There are 2 ways you can do this. One way is to simply take the valve and flip it over. That will allow only a few drops in at a time. Another way is to take the valve, putting your middle finger and your pointer finger on either ends of the valve and your thumb on the opposite side, and very slowly turn until you just get 1 or maybe 2 drops out, and then swirl that around. Now you can see that this is initially pink, but then it fades away. So I'm not quite at my end point. So I'm going to try adding another drop here and see if I can get that color to stay. And I'm going to keep doing that until the color persists. You may find that you are getting very close and you don't want to worry about overshooting. I recommend going ahead and writing down the number between each drop, and then if you overshoot, you can write down the number for the last one rather than the one that you overshot with. Once it turns pink and it seems to be staying, you want to make sure that it stays for at least 30 seconds to a minute. Any shade of pink, in my opinion, is pink enough, because phenolphthalein does not turn pink until it is above a pH of 8. So you really have hit your equilibrium. You really have hit your end point at this point. Some professors prefer to see something a little bit darker, but as long as that pink persists, you're definitely at your endpoint. So this should be our endpoint of this particular titration. I'm going to show you what happens when we shoot past that endpoint so that you can see why it's important to have a very pale pink. So this is a really good endpoint here. I'm going to add just a couple more drops. That was about 3 drops. And you still have what you would call a light pink color, but it is quite a bit darker than what you had before. So that means that you've moved quite a bit in the pH range. If I called this my end point and then just added a few more drops, I get a color change, but not much. So that means that I don't have as much precision once I get away from that very first pale pink color. Now if we look at this pink here, this still looks like a light pink. Let me add a whole squirt here. That didn't change a whole lot in color, but my volume changed a good milliliter or so, which really is going to affect my calculation of the molarity. So I need to be sure that I'm using the palest pink possible.
You will be able to use several different flasks for this, but if you have to repeat a trial, you might have to reuse one of your flasks. Make sure that you number your flasks or provide some other label for them so you know which flasks you have used and which ones you haven't. You can repeat using a flask, but make sure you rinse it thoroughly several times with deionized water to remove all of the residual acid or base that are present. You're also going to want to take a picture of your 3 best endpoints. So make sure that you take a picture before you empty out the flasks. When you are done using your burette, empty them, rinse them several times with deionized water, allowing the deionized water to flow through the open stopcock. Leave the stopcock open, turn the burette upside down, and reattach it to the burette stand so that it will be ready for the next class. For this lab, we are going to be using the concept of molarity. Molarity is a concentration expressed in moles of solute over liters of solution, and we will be working with an aqueous or water-based solution. We are going to use the known molarity of the sodium hydroxide and the volume of the sodium hydroxide in order to determine the moles of sodium hydroxide in this mixture. Remember that as a mixture, we can't use the mass because the mass includes both water and sodium hydroxide. So using the mass and the molar weight would end up resulting in a very wrong answer. So if we take our equation, molarity equals moles over volume, and rearrange it, we will find that the moles of the base is equal to the molarity times the volume in liters. Our reaction that we're doing is combining sodium hydroxide and hydrochloric acid. This is a neutralization reaction that will produce water and the salt sodium chloride. Notice that in this balanced reaction, all of the coefficients are 1, which means the ratio of each compound to the next is a 1-to-1 ratio, and that will be really helpful. You will be provided with the molarity of your sodium hydroxide, and it probably won't be the same as the one that I am showing here. But let's assume the concentration we have is 0.1834 moles per liter. Then let's assume that we used 21.38 milliliters of solution. We are going to need to find the moles of sodium hydroxide. So we're going to use the formula molarity times volume. But we need our volume in liters to find the moles. This is the number of moles of sodium hydroxide. But according to our equation, every time we use a unit of sodium hydroxide, we are using the exact same unit
of hydrochloric acid. So now that we know the moles of hydrochloric acid, we just need the volume of hydrochloric acid that reacted with this. So let's say that the volume of our hydrochloric acid was 12.95. We will simply divide the moles of hydrochloric acid by the volume in liters, and this will give us our concentration in moles per liter. You'll do the same calculation for each of your trials that you repeat, and you want your calculations to end up with your answers very close together so that you have agreement in the first, second, and if possible, the third decimal place. So if I had 0.3030, this would be very close to the concentration for this trial, and I would say that those are very close. But if I had 0.3095, that's quite a bit different, and I want to not use that trial and do a different trial. Since you will be repeating this calculation many times, it may be helpful to recognize that you can combine all of this into a simple calculation. We took the molarity of the base times the volume of the base and said that number of moles was equal to the molarity of the acid times the volume of the acid. Now this is only true because we have a 1-to-1 ratio. Since we are looking for the concentration of the acid, we can rearrange this equation to say that the molarity is going to be equal to the molarity of the base, the NaOH, times the volume of the base divided by the volume of the acid.